So continuing chapter 20, focus on this Nerst equation, talk a little bit more about it and do a calculation with it so you can kind of see where it fits in. So good or bad news is the Nerst equation is not on your formula sheet. They don't expect you to know it for the AP test, but it's a very valuable equation. You can refer to it when you have different concentrations, because again, if we're not at standard conditions, we're not at 1 molar. And I'll show you that in this example. So you can use it as an explanation. And on my test, I'm going to give you this formula, so you don't need to memorize it, but you need to know how to use it. Okay, so if there's any consolation with that. So this is the problem I want to work with the Nerst equation. So what is the value of E cell of the following galvanic cell at 25 degrees Celsius? So please understand that you don't see a degree sign, so it's not standard conditions. So you just need to be careful about that in terms of what E cell are you asked to calculate. So here is my line notation, and please understand that I know this is not at standard conditions because I have concentrations given. If we are not at 1 molar, Ag is at standard condition, these two are not. So I have to use the Nerst equation, and that's how I know I have to use the Nerst equation. If nothing is listed in the line notation, you could assume it's 1 molar. Okay, so Fe2 plus is then going to Fe3 plus, so it is losing 1 electron. Ag is going from a +1 state to a 0 state, so it's gaining an electron. And both of these are 1 electron, so I don't need to worry about doubling or anything like that. So if I take my table, okay, and look up Fe2 to 3, I will find that it is 0.77 volts. But since this is going the opposite way, I have to write this as negative 0.77 volts. Ag going from a +1 state to a 0 state is here, up here, and it is higher. It is at 0.80 volts. So when I add these two together, I get Fe2 plus Ag plus goes to Fe3 plus Ag, and my voltage comes out to be 0.03 volts. So that's my E cell under standard conditions. So I write a little degree sign. All right, so I want to find it under non-standard conditions, so I have to use the Nerst equation. So that's going to be 0.03 volts, because again, it is the E cell under standard conditions, minus 0.0592 over the number of moles of electrons being transferred. It is 1, so it is over 1. I'm going to take the log of my Q. Well, what is on my product side is Fe3 plus and Ag, but realize Ag is a solid, so that can't be included in the Q. So you have Fe3 plus on the top, and then both of these are aqueous ions, so they have a concentration, and I was given a concentration in the original problem. So I have Fe2 plus, and I have Ag plus, and everything is 1-to-1 to make my life so much easier. Okay, so this is going to be 0.2 molar on the top, and this is going to be 0.1 molar and 1 molar on the bottom from the from the equation, the line notation I was given. Well, the Q comes out to be 2 when you do that, okay? So I end up with 0.03 volts minus, when you do all of this, you take the log of 2 and multiply this out, you get a 0.0178 volts. When you subtract those numbers, you get 0.012 volts as your final answer. So that's under non-standard conditions. If it was standard conditions, you would end up with 0.03 volts. Well, there's an interesting pattern you find with E cell under non-standard conditions compared to E cell under standard conditions. And it has to do with the Q, right? So the Q here was greater than 2. Okay, so it's greater than 1. So that means I have more products than I do reactants in terms of this Q value. Well, if I have more products than I do reactants, in terms of the E cell under non-standard conditions, it's always going to be less than. It's always going to be less than. And if the Q is less than 1, meaning it stays as reactants, my E cell is going to be greater than the standard conditions, okay? And it has to do with, again, the fact that your Q here, you are subtracting it from the standard conditions. Whether or not that's going to be a positive or a negative value is going to determine which way this naturally goes. Okay, so this holds pretty true. So if you see your Q is greater than 1, you know your E cell is going to be less than that. And you could use that as an explanation as to if the E cell is going to be greater or less than standard conditions. So again, you don't need to know the Nerst equation, but I'm still going to have you do some of the math associated with it because I think it's a very valuable thing to know. So with this idea of Q, okay, and products and reactants, what you could be asked is, well, what if I increase the concentration of my reactants? Okay, if I increase my concentration of my reactants. So what's that going to do to the overall cell potential going on here? Well, there is a point at which this cell will run out, meaning you won't have enough reactants to keep making products. So you will see the E cell start to keep going down. But if I increase the reactants, okay, think of, again, our understanding of shifting reactions. I'm going to make more products. So if I make more product, my Q is going to get larger. So then for my E cell is always going to be a little bit lower because of that. So as the cell starts to keep going, you're going to see the voltage keep decreasing and decreasing and decreasing. Eventually, you're going to get the E to exactly 0, and that's when the cell is pretty much done, and you have reached equilibrium, and there's no net reaction because you're not going forward and you're not going reverse. So one little side note is batteries. And there's a huge focus on batteries, of course, now in our everyday lives with our cell phones, with now electric cars and other industries that are using different technologies to kind of promote more and more electrical current. So batteries are a series of galvanic cells, okay? And again, if you go into physics, you'll talk about you know, putting things in series and parallel and stuff like that. So your book, unfortunately, because of when it was published, does not have a lot of stuff on the newer technology because, again, some of these book publishers, they don't have as much up-to-date information. So I'll provide some links and some other things you could look at for batteries because that's a huge industry now in terms of solar panels and also how to store that energy into batteries in electric cars, in our cell phones, making them smaller and more efficient. So these are just some common ones. Lead storage batteries, dry cell batteries, again, used to be the more common batteries. I don't know now if the batteries you have in your phones are now replacing those in terms of how common are they in terms of how we're used. And then something called a fuel cell. Again, some people are looking at using hydrogen and oxygen, combining those to make water as a way to power cars as well. So not too much emphasis, but it is kind of a summary of what you have on your book.